Okay, everyone, so welcome after the break. I will just check if it's being recorded. Okay, it's recorded. So we are going to continue. So maybe there's one thing I'm going to mention before we move on to the data frames. So Julia has great integration with programming languages. And here at the end of this introductory Jupyter notebook, you can find some examples. So I just wanted to know that in Julia, we can load things such as Python library. Uh, and there are indeed two Julia libraries for that. One is called PyCall, the other is called Python call. The Python call is kind of newer. PyCall is slightly more popular, but nevertheless, if you have any code in Python, you can easily load this library in Julia. So there is a very simple here example with calling NumPy, Python NumPy from Julia, and basically as simple as that, you can write PyImport, and you can load any Python library into Julia. And if you know NumPy, the NumPy itself has command named zeros. And for example, this creates an arrays of 0. This is a D type from NumPy. So this is NumPy D type, say int32. And if you execute it, you get a Julia matrix of int32 values. So this is a quite seamless integration. And basically, so there, like I mentioned, there are two libraries, Python call. There are tiny differences, but basically you can have a seamless integration and navigation between Julia and Python. So you can load any Python library into Julia, for example, for visualization. We do not use Python like for number crunching because Julia is much faster, but for data visualization, Python is great. Sometimes also some specific algorithms could be only implemented in Python. Usually in Python, they are implemented in C anyway, but some specific algorithms could have nice Python libraries. Then you can just load into Julia. And so this is very nice when something is missing. And when I'm doing my data analytics, my research projects, I can see that from time to time. I can see that from time to time that I'm using this integration. So here's, for example, a piece of code. So you have a string macro pi, and the string macro pi, inside the string you can put any piece of my Python code. So you have here a piece of Python code that is being called from Julia. And if you execute that, then you're getting a Julia object. So basically you can navigate between Py, and there are libraries for those. There are, of course, some nuances, how it works, how it doesn't, and so on, but you can easily navigate. Another language, which is great for statistics, is a language named R. And there is a package named rcall. So here's a piece of code that is created. This is a multivariate normal distribution. So these are essentially correlated streams of normally distributed random numbers. You have here some variation and covariance matrix. And if we generate it, you can use rcall library and any packages from R installation to perform plotting. Okay, so if you have R installation, you can use R to make to plot graphs in Julia. Okay, and there are also integration for other languages, but if we think about data visualization, data analysis, some broad mathematics, usually it ends like this, that you can. Okay, so this was compiling something. I will be not trying it because I might have switched some R version, so sometimes configuration is tricky. But what you can do, you can write, this is a macro, add library, load library ggplot. And then so this is a type of algebra of graphics library. And then you can write just ggplot code that is performing this code. So you can mix Julia code and R code. This is one pattern. And the second pattern for mixing Julia code and R code is via R text macro. Like you have Py text macro in front of text, and you can mix Julia and Python code. You can use R macro to mix Julia and R code. And indeed, here's the variable df. This is a data frame. Exactly what is data frame we'll discuss in a minute. But this is a piece of data, a table of data, and here this $sign is interpolation between Julia and R. So in some contexts, interpolation operator can be sending an object between programming languages. And it works. As you can see, this integration code is very simple to write. So this is worth noting. And this is also very convincing if you are coming from other programming languages and you need to some very specific visualization. With Julia, you can reuse existing libraries. But now we are going to move to tabular data. So this time I'm going to open another workbook. So we go to day 1B, working with tabular data. So this will be essentially about data frames. So a data frame is a structure where you have a table with a set of columns and a set of rows, and columns have different data types. And of course, this is something best illustrated with examples. So, yep. Mhm. Okay, there. Just for people listening, the question whether it's possible to work Julia with R. As far as I know, there is a library to call Julia for R. I've never used it. The library working quite well for calling Julia from Python. So you can call any piece of code from Julia to Python. Uh, my experience from calling Julia from Python, that it's kind harder to replicate the environment. So if you are moving from computer to computer, sometimes configuration tends to be hacky, and maybe it has been hackish, maybe it has improved, but calling other languages from Julia tends to be much easier than calling Julia from other languages. I think this is changing, but this is the last. There is a library. There is a library for calling Julia from R, but I've never used it. Mhm. The second question. No, Julia in virtual environment only only allows us to manage Julia packages. However, if you are using, for example, the PyCall package, there is a Julia package which is named Conda. And Julia package Conda is providing interface to the Python Conda package manager. So you can do for example, like Conda list. Okay, and then you can list, for example, the Python's installed packages. But Python, of course, is coming with its own package manager. So Julia is providing Julia interfaces for managing of Python packages, but still you can work with Julia. You can have Julia working with any Python installation, but still this is a separate Python installation because obviously Python is not a part of Julia. It has its own ecosystem with its own advantages and disadvantages. So you can manage this programmatically. You can do it with Julia, but still this is a separate Python installation. And also configuration of Python installation is not of part of Julia virtual environment. So Julia virtual environment allows you to manage all the Julia packages and their configuration, but unfortunately, it does not allow you to manage Python packages because it's part of, say, Anaconda or Easy Install or PIP and so on. There's a total mess. What does it mean, to have a Python installation? So, yep. Yeah, so Python has its own virtual environments. So conda list could work in a specific Python environment, and you can define what Python environment you want to use conda. And Julia has its own environment, and they two exist independently. Uh, because like Python is not a subset of Julia, and Julia is not a subset of Python. So these are separate products. But so one is conda, and so conda, the conda package is working with the pycall, and there is a second library. I just want to make you aware. There is a second, because if you do integration, worth to knowing, there is a slightly more modern library. It's slightly less popular, but it's becoming even more popular. There is a library named Python call and corresponding library Julia call. So Python call is also for calling Python from Julia, and Julia call is for calling Julia from Python. Okay, so if you need to do some integration, this is another set of libraries, another set of library to look at. And this library is also using conda, but different package manager. I think it's called conda pkg. It has slightly different name than the one I showed. Okay, but anyway, you can call it, but each time this is a separate virtual environment. Okay, so let's go now to the data frames. Thanks for all the questions. So we'll be looking at a database of chess puzzles. So there is a lichess software, and people have played many chess games. And since whatever was written in those chess game has been collected, the last few moves before the chess game ended of real players have been changed into chess puzzles. Okay, so these are real games of chess, and the last few moves of those games have been converted into chess puzzles. And we'll be using this database of puzzles. And for these examples, we'll need to load quite a significant set of libraries. Later, I'm going to discuss which library is doing what. But basically, we have here libraries. We'll make a simple regression model to see what depends on what. The data is available here in Parquet format. So Apache Parquet is a format for tabular data. This is just an example of just example of data format. So this is format very popular in big data systems. Another possible format could be Apache Arrow, or it could be a comma separated files. So what we are going to do first, we are going to load this Parquet file, because then once we load the file, I can discuss what about those chess puzzles. So how do they look like? So we load the file with the chess puzzles, and here we have Parquet dataset, which is generating an object representing a dataset. Now, Julia has a DataFrames library that is relying on something which is called tables.gl interface. Okay, and tables.gl is a general interface in Julia for any type of tabular data. Everything here is, of course, a Julia package somewhere on GitHub. So you might have already noted that whenever I start something with Julia, this is in a package. So this is a general interface for tabular data. You don't use that, but so this is for package authors. But the outcome of that is basically there are several libraries that can ingest tabular data, and via the tables.gl interface, they can be converted between different tabular formats. And here we're going to work with DataFrames format. Okay, so we have this data source, and now we are going to change it as a data frame. So this is probably the first thing we are going to discuss. So what is this data frame object? So this is a tabular, this is a piece of tabular data that is defined by row and columns. As you can see, each column has its own set of data types. So for example, so these are the mating, so these are the positions few moves before the mate. What you are seeing here is we have here the last we have here the last move of the opponent, first mating move, response of the opponent, and the second mating move. So this is a puzzle made in two. Of course, we could display this puzzle. So this is available on Lichess. Now, this puzzle has several properties. We have selected only a subset of columns that we are going to use for this exercise. So here there are moves to solve the chess puzzle. So this one is find a mate in two. This is the rating. So this rating is calculated in this way that this puzzle is made online, and several people have played this puzzle. So this puzzle was played by 505 people. Okay, so 505 people tried to solve this puzzle, and this rating is assumed that the puzzle game is played about a player having some ratings, because player in this lichess.org, they have their ratings. And this is kind of like player versus the puzzle, whether the player can win in the end, some adjusted time or not. And then it's using the standard rating calculation system. So this is here XStar. So it's using the Glico rating system. And this is basically difficulty of puzzle. So if only strong players can solve the puzzle, it means that the rating of the puzzle is going to increase. And if very weak players can solve the puzzle, this is going to decrease. So more or less, this puzzle we have here is solvable on average by a player having, an average is not exact because this is rating calculation system, but on average it's being can be solved by a player having a rating of 1000. This puzzle can be solved by a player rating of 1400, and so on. Okay, so and then why people are solving the puzzle, attacking the puzzles, their rating, so the difficulty rating of the puzzle is being updated. And of course, the bigger the rating, the more difficult the puzzle. So I could say this is a puzzle designed for players having ratings around 1600. Okay, so this is more or less good difficulty. Why this puzzle is definitely for beginner players, because if you play chess, then you know that the rating 1000 is a low one. Okay, so this is a puzzle for beginners, and this is a puzzle for quite advanced users. Then we have the popularity. So the popularity is some standardized measure how, when people see this puzzle, how they are eager to start working on it, solving on it. So this is a measure between minus 100 and 100, and this is the number of times the puzzle has been played. Okay, so because then people select decide to play this puzzle, but people can send via links, discuss on forums, and so on. So this is the time that the puzzle actually has been played. Now these are the terms that describe what is the puzzle about. Okay, so one side has an advantage. It's a middle game, and it's a short puzzle. So those labels, they have been first generated by their system, and then players can vote or add new terms, new description to puzzle. So we have like plenty of description to each puzzle. And last but not least, we have information about what opening was played. If you play chess, you know that some openings lead to very boring game, why some other opening leads to very exciting and kind of risky game, which might generate more interesting puzzle information, because all those puzzles have been constructed from real games of some players. Okay, and we'll be asking the question, what is influencing the popularity of the puzzle? Okay, so our goal will be to understand on the base of this data what contributes to popularity of the puzzle. The original data have more columns. Like, for example, this is a binary encoded the full position of all pieces on the board, and we are not going not going to use it. There is a game URL, so you could indeed find the exact game that was used for the puzzle. Okay, because this is a real world game, so blah, blah, blah. I think if I open it, okay, I can have the URL, and I can see what was played during the game, from which game this chess puzzle, from which game this chess puzzle came, uh, and so on. And I think I have URL opening tag, so I can find information about what was the opening, like Sicilian defense, dragon variation, and so on. Okay, and my goal with this data is to understand, so we'll do an exercise with such data to understand what contributes to popularity of the data. So we loaded this data from Parquet format. As well, we could use, for example, CSV file. So there is a Julia package which is named csv.gl. We'll use it at some other exercise with comma separated values. So because we'll use CSV somewhere else during the course, here we Spark it. And we have the data. Okay, so you can see this is shown as a data frame. Now we'll be manipulating this data frame. Just for introduction and additional, you can, of course, in Julia, I could construct a data frame from any data. So more like hello world example. I could write something like my data frame equals data frame, and then you have column A with values from 1 to 4, column B with values, say, A. So these are characters, A to D, and the column C with 4 random values. Okay, so this is how a data frame looks like. So data frame allows us to cleverly group several vectors, because each column is kind of a vector. Each column has its type. Okay, but this we treat as tabular data. And as you can get, as you know, all the data is in business, like operational data of companies. They usually come as such tabular data, and they have this format. So data frames are extremely popular as of today. For Python, there is library named Pandas, and for Julia, there is the data frames library that we are going to talk about today. Okay, so we loaded. So we loaded the we've loaded the chess puzzle. Okay, so what do we want to do? We'll try to understand what's inside the data. And the first thing we can do, we have a function which is named describe. It has some parameters, but we are just going to use standard parameters, and we can look what is inside the data. So it goes through all columns and calculates some statistics. So the column moves is of type string. So probably mean and median does not make any sense. And missing is the number of missing values. So sometimes in the data, we have missing values, and this is a specific value in a data frame. So in the data frames, sometimes we have missing values. This is very often related to situation when the data is not available. For example, if you have people applying for credits, and for example, a customer asks us the question, have you ever used some narcotics or legal substances? A customer could refuse. Okay, and then you have a missing value. So you do not have a value. So we do not have any missing here. So all data is complete. So the column moves and minimum and maximum values. Then we have rating. So we can see that average rating is 1500. So this is the average difficulty of the puzzle. So the average difficulty of our puzzle is 1500, and the minimum is 550, and the maximum is 2900. So this is the puzzle that probably only the strongest chess players could solve. Now we have the popularity, and the popularity is between -100 and maximum is 171. So I'm not sure exactly how this was calculated. I think in the description of data it was between 1 and 100, but I'm not sure. Popularity, yeah, it should be 100 and -100, and depends on up votes and down votes. As you can guess, sometimes in the data, we might have some error. So we will not be correcting that. But if it was our business or research project, now it would be the time maybe to find these records, why some pieces of data have higher popularity than data specification. We could perhaps list those data. So let's do this as an exercise. So I'm looking at the specification of the data, and I'm seeing something that I kind of do not trust. Okay, let's go to this data frame. Okay, so if I have a data, so suppose since I'm seeing in the documentation that the popularity should be 100, and I'm seeing 171. For an example, what I might want to do, I might, for example, want to check how many games have this popularity higher than 100, or maybe what is the distribution of popularity. I could do, for example, histogram. And if I reference anything in a data frame, I type the name of the data frame and dot the name of the column. So here it's popularity, and it's enough to type P and then press tab, so it has the highlighting. Okay, so it knows what I might want to type. And then what I'm going to see, I'm going to see a simple histogram. So you see the popularity is up to 100, and it should be up to 100. It looks like it might make sense, but there is most likely very single observation that is beyond the limit. So this is some kind of error in the data. Okay, because you could see from the documentation, so there is a set of puzzles that have been downvoted, but usually people liked puzzles and they upvote them. So usually the puzzles are liked by people. And there is a typical popularity is about, I think, 90. Okay, but I could see that there are some cases with popularity I don't like over 100. So I would like to see how many such cases are and how do they look like. So how to filter out? So we can do this in the following way. So we have popularity. So popularity is a vector. Okay, so it's a vector. When we have a data frame, each column is just a vector. And what I might want to do, I might want to select, I might want to see which are the elements that have popularity greater than 100. Okay, and what's going to happen if I'm going to do like this? Is this valid algebra operation? Can you compare a vector to a scalar? No. And in Python, this would have worked, but not in Julia. Anything is not a valid mathematical operation, this is going to fail. And this works like this, that in Julia, we use something which is broadcasting, and we always need to control it. So what I would like to do, what operation would be defined would be to compare each element of the vector against a scalar. Okay, you agree? It makes sense, comparing each element of vector to a scalar. And in order, so this is called broadcasting. So you want to broadcast the comparison operations over all elements of vectors. And in most programming languages, in this case, you would be writing a for loop. Okay, you agree? You would be iterating with a for loop. With Julia, it's nicer because we have a broadcasting operator, a dot. And in most cases, you can replace when you are working with vectors. In most cases, you can replace some strange some writing loops with dot. So dot means apply each matching element from each vector. It could be two vectors or a vector or a scalar. And the nice thing is that dot, it's element of syntax of its own. So what it means that, for example, if you define a function such as f a and b equals a lower than b, then returns a, otherwise it returns b plus 5. Okay, this is we have this ternary operator in Julia. If a lesser than b, return a, otherwise return b plus 5. Okay, and or maybe plus 500, so it's easier to see. And if I have a function like this, I could of course write. Sorry, I got lost here. Where is my cell? I could of course write something like f of from 3 and 4. Okay, it's going to work. But if I'm going to do with vectors, okay, a comparison for vectors the same length is defined. But if I do it for vector a scalar, so 3.5, okay, I cannot do it. But now, if I want to vectorize something in Julia, I could do a loop and make original version of the function over all elements. But if I add dot, this is as good to say I want to vectorize this function. So any function you define, any operator you see in Julia can be vectorized by adding a dot. And if it's a function, you are adding the dot after the function. And if it's a two-argument operator, you add the dot just before the operator. Okay, and this works. Okay, so this is easy as that. That you can replace loop with just a dot. So that's why I'm comparing all elements versus 100. So I'm adding this dot, and now I can find the elements of the data frame df. I select the rows that have this high popularity, and for example, all columns. So if you want to select something from a data frame, you can provide the row indices or binary value, whether the row is selected or not. And here I'm providing the list of columns, and the column matches all columns. And I can see that in the data set, there was only one such row that is an outlier. And as you know, if you work with real data set, you always have stupid outlier row. I could have corrected it now, but I would just stay with it. I would say, okay, it's this one single outlier. Or okay, maybe let's delete it. Let's see, maybe it will be nicer. So how can we delete it? So what I can write, we have a command named filter. Okay, and you can write something like filter. And okay, row. So I need to provide a function for filtering. There will be also other examples. A function that takes row, and I could write row popularity greater than 100 and this data frame. Okay, so I'm having all rows with this popularity, but I could select also all the rows that have good popularity, lower than 100. Okay, and if I want to, this are the only rows I want to be left in the data frame. We have a special another function which is called with exclamation mark. And basically exclamation mark in Julia, it's a different function name. So we have a function which is named filter exclamation mark. Okay, and filter exclamation mark will be filtering those will be filtering rows, but also simultaneously modifying the data frame. So if I do it like this, oh, I cannot delete it because it's in this Parquet underlying format. So I would need to still provide a copy. I can do, you can delete it or not, then I will just assign to a new variable. Okay, so I just copied all the data because the underlying format of the data was Parquet. So you might also leave that, or we could create a view. I will show that later. So we have one outlier. We can remove it or not. Let's move further. So we have here other fields. So we have themes. So it starts from advanced pawn, ends up opening. We have opening family starting from Alekin to Accord and so on. Okay, so we can look at the different values. So one is rating. So when we try to print rating, we are make a histogram of rating. We can see that this is distribution of rating, and the standard rating is 1500. The most popular rating is 1500. It's because in this rating algorithm, when you start with a game, initially it's being rated to 1500 if it's not played yet. Okay, so the default rating is 1500, and that's probably why this is the one the most common. And then players are going to play against this game, and the rating of this game is going to either increase or decrease. So what I might want to do, there will be more filters. I might want to say, okay, so if this is the default rating, and most likely this is only for the games that have not have been played, or it's count of outlier. So maybe I would like to say histogram with all the ratings that are not equal to 1500. And this is funny code because, so I will first explain it, how it works. So if I have the vector rating, okay, so this is a vector. And suppose I want to get rid of all the games that are exactly 1500. So what I could do, I could do filter of this row, filter from this vector. And now I need to provide filtering function. Okay, so we are providing filtering function as a lambda function. You know concept of lambda function, right? So the previous one was also lambda. So this one, sorry, forgot to tell you. So the one I used here, this is a lambda function. The parameter of this lambda function was row, and this is the body of the lambda function. Okay, so I've provided a lambda function. So suppose now I would like to filter all rows that do not have a rating of 50, 100. So I could do the following. I could say element X, where X not equal, you could type slash unequal, enter. And then we have the LaTeX symbols for inequality, 115, and the rating. Okay, so this displays all the ratings that are not equal to 1500. Now, we have very often lambda function that do very simple things, like comparing something for greatness, equality, or inequality. Okay, so we have So we have very common this type of lambda functions. And to make our life simpler, Julia is providing a kind of synthetic sugar, a set of already predefined lambda functions for such common cases. And I can shorten this lambda function to the following code. Okay, so I can say filter not equal, this will behave like a lambda function, not equal 1500. Okay, so for very common operations, like you could say greater there, equal there, what is this not equal 1500? Because it looks kind of funny. Okay, so this is something which called fixed to operator. Okay, but this is going to behave like a lambda function. So this is the type of function. Okay, so not equal 1500 DF rating. Very nice syntax. So at first maybe kind of strange to type, but keeps your code very short and very nicely readable. And it's also very efficient. So the way it's implemented is it's really fast. So if you do it over huge tables, it's a really efficient implementation. Okay, so in this way, we know how to do a histogram when I would like to filter this. So I could do histogram, filter different than 1500 DF rating. And here I have ratings without 1500. I can also plot a histogram for popularity. So I might want to see what is the popularity. So there was one outlier that I removed. And we can also plot a histogram for the number of plays. So this is a typical visual exploration of data. So if you get a new data set, you want to see what is inside the data set. Now, I'm plotting here 4 histograms, and I want to combine them all into one plot. So I could say I want to combine it into layout 4 by 1. So 4 rows, 1 column, and the size 500 by 750 pixels. Yeah, I could make it maybe 900, so it's bigger. I'm not sure if then I can display it. Oh, here it is. Okay, so this is 1, 2, 3, this popularity thing. I have removed the single observation with the outlier popularity. So now it looks better. And number of plays. So you can see that this is you can see that almost all games have never been played, and there are some games that have been played hundreds, thousands of times. Okay, so this function, so maybe we could plot logarithms instead of that, but this is this funny distribution for this. Now, in the next column, we have tails. By the way, earlier it was parquet data set, but I just removed a single row and this underlying data set didn't support it. So I have copied it. So I now have a vector of strings. So you could be also, depending if you didn't remove this row, you could see here a vector of some parquet data set. But and anyway, the times is a vector of 500,000 strings because we have like 500,000 observations in the data set. So now we would like to understand what is inside those types. So what we can do, we could make split. So if you have a piece of string, okay, split is using spaces or any other defined character to slash string into pieces. Okay, so we are slashing the string into pieces. So here we have split. First is going to take first row. So if I write something like first def, maybe dot time. So first takes a first row of the data frame. And by the way, first row of data frame is also displayed as a data frame, but it's of different data type. It's data frame row. Okay, or I can take a first element of a vector, and it's first element of the vector. So you can split it. Okay, so if you have times, then if you split it, you have a vector of strings. Even more precisely, if you remember the thing about matrices that I told you, it's you can be non-allocating in Julia. Okay, so you can avoid allocation. The same is about strings. So instead of copying this old data, it's making a substring of string. Okay, because if you are slashing a long string by spaces, you do not need to copy all of the data in memory. So depending on how you write your code, Julia might try to avoid copying. Anyway, what I could do, I could find out what are the old terms in the data set. So I'm creating here a list of terms. So this is a vector. I'm splitting each element, and then I'm collecting. I have a total list of 2 million times. Of course, there are duplicates because it's a vector of 2 million elements. So of course, there are duplicates, but I might want to know how often each time can be found in the data set. Okay, so you have many times. And I would like to know which times are popular. So what I do, I can do a frequency table. And there is a package that we loaded at the beginning, which was named frequency tables. It was freq tables. So now we can use it, and we can see what is popularity of each of the tables. Okay, so we have the frequency table. Now, if we have the popularity, again, since it's a table, it's usually, if it doesn't fit the screen, it's doing those dots and so on, because we do not want to flood the screen with text. Okay, but usually we are interested what is the most popular. So what we can do, if we have these frequency tables, this frequency table is, again, it's some specific type of Julia object, but we can sort it. So if we have a frequency table, oh, by the way, what is the type of frequency table? Just to show you, type of. Okay, so this is quite detailed. This is quite detailed composite type. It's not specific for frequency tables, but it's nicely displayed. Okay, so this is it. But I can sort it. So if I sort it, and I can sort it in reverse order to see what's most popular. So the most popular theme does not mean it's the most popular puzzle, but the most popular theme is middle game. So most of those puzzles are from middle game. What it means is that when people are playing on chess, usually they complete the game in the middle game. Like usually somebody gets made not in few beginner moves, but usually also the games do not get into end game. Short, so most of the time, most of the puzzles have just few moves. Advantage, so lots of puzzles have some advantage. Crashing, so they are probably, you know, making very hard situation for one side, and so on. Okay, so let's see which puzzles are with mating, and we can see that we have 14 times which have the word mate, and in particular, so how does it work? Does it work? T 40 in times if contains lowercase t mate. So here we are generating a vector of elements that contain. So this is a generator. It's like this. This is a comprehension. Yeah, so this code is somehow more difficult now. Okay, so this is making a generator. Why is a generator? Because I do not want to materialize this list because it might be very long or due performance reason. So this is generating. So this is making a generator of elements of time of those times that in lowercase contains the word mate. It's similar to Python. In Python, you have similar generators. You remember such generators in Python? They have very similar syntax. I think if I copy paste it into Python with regard that contains a lowercase would be slightly differently, it would work. Okay, but this is very Pythonic syntax. So this is generating the times. This is making a unique list. So it's selecting the unique elements. And this is sorting. Sorting so for display. So I can see there. So I can see we have we have 14 types of mating puzzles. And next, what we are going to do to this data frames, we are going to add. So we can have mate in 1, mate in 2, mate in 3, mate in 4, mate in 5, or some other puzzle. Because some puzzles are like mate in 10 or whatever. But our feeling is that the complexity of the puzzle is very important for popularity. Like, come on, do you like to solve puzzle mate in 10? Okay, mate in 2 or mate in 3 is nice, but usually this is what people are looking for. You do not want your puzzle, it's for my experience, I do not like the puzzle mate in 1. It's for beginners, obviously, but puzzles mate in 2 or mate in 3 can be very nice and very tricky. You agree, I guess? So they are really fun. They are really fun to solve. So, and this is my question: how is this determining the popularity? So, if I want to include that in the model, so we'll be doing some simple multiple regression model. So, if I want to put this into my regression model, I need to change those into binary variables. So I'm going to have the following binary variable. Either it will be mate in 1, in 2, 3, 4, 5, or it will be some other type of mate. So this is what I do now. For I in 1 to 5, if mate in 1, 2, 3, 4, 5. And now it's tricky. So I need to explain this. So if I have something like contains and say I have some text made in for dovetail made. Okay, made in 1. If I do this, this works. But if I have a vector of strings, because my data set is a vector of strings, obviously this cannot work because contains operation is working on strings. What do I do? Do I write a loop in Julia? No, in Julia we do not need to write loop. I add a dot, okay? I vectorize. So this really, in many occasions, you will see this small dot that is going to make a big difference, because a scalar operation is going to be turned on vectorized operation. By the way, if you use Python, if you use NumPy, very often you write operation and it's used as vectorized, but you never have control. I really do not like it for mathematics. You know, you write something in Python NumPy, everything is treated as vectorized, but you never know. So you are, you know, multiplying two matrices. And come on, is it matrix multiplication or element by element, some type of tensor multiplication? You kind of never know. Of course, there is like mul function, blah, 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 but it's very ugly. I really prefer, you know, multiplication is algebra because it's mathematics, wants to multiply element by element at a dot because you vectorize it. Okay, so I really love this dot. So this is it. So this is generating entire column of zeros and ones for each element of Thames. So this very short code, in a very nice, elegant way, is adding me 5 columns describing the number of moves for the mate. So if I display this data frame now, I have row, I have moves to get the mate, rating, popularity, number of times of played, times, opening family, and whether it's mate in Z1, mate in 2, mate in 3, mate in 5, mate in 4, mate in 5, or probably a mate in some different types of moves. So I would assume, although those categories are being made by users voting, so there are issues about data quality there, but basically let us assume that this means this means that we have either in 1, 2, 3, 4, or 5 or more moves. Okay, we could also calculate moves in a different way. There is a data inconsistency. We are going to ignore it, but just to show how to find it. Because here we see the moves. Okay, 1, 2, 3, 4. The first move is the move of opponent. This is how the data set is being defined. This is the first move of mating solution, response of the opponent, the second move of the mating solution. Okay, and there are many examples. So this is mate in 1. The last move of the opponent, first and the only move of the mating solution. Or, for example, we have blah, blah, blah. Do we have anything longer? So this is mate in 3. First move of the opponent, first move of the solution, second move, response of the opponent, second move of the solution, another response of the opponent, mating move. Okay, so this is, and this exposed king. H1, A1, so it was some rook probably being moved, or a queen, who knows. Okay, yeah, sure. Good, thank you. Okay, yeah, because maybe it's maybe it's easy. Okay, so here we see the moves, so we can calculate and build a histogram of the moves. Okay, if we have a data frame, then we could select a subset of columns, and we have a special selector node that is kind of negative selection, and this is kind of funny. I could have a vector of elements 1 to 4, and I could write like v not 2 to 3. And any tricks like this work. Okay, so we have a negative selector. Okay, we have a negative selector. So now Select with exclamation mark, it's a version of select function that is modifying the argument. So this is a naming convention in Julia. Whenever you see an exclamation mark, it means that the function is mutating its argument. Okay, so exclamation mark, okay, this is going to mutate. So we have some data frame as an argument, and yeah, and what it means, remove two columns. Okay, so I have the data frame in two columns. Moreover, this data frame is already mutated. So if the next time it's not going to work because the columns are already not there because I've removed them. So maybe I will now just for a second comment that out because I already removed them. So this is the set of columns I have now in the data frame. Okay, so my question is, how does the type of mating puzzle affect the puzzle popularity? So I would like to build some simple linear regression model to explain how is one affected by the other. Okay, so I'm creating here a model. So this is the variable representing model, and I'm using the package which is named glm.gl, which stands for generalized linear model. So I have here a package for linear models. Normally, it's using the ordinary least square method to find the parameters of the model. Okay, so we have the model. And now this is again a macro. Okay, so this is a macro. So if we have some time at the end of this lecture, I will slightly discuss how these macros work. So this macro is basically taking a set of arguments for model specification. If you've been using R, you could see similar context. So it means explain popularity with using the variables made in one, 2, 3, 4, 5. Okay, so this is our model specification. Of course, we could be adding other variables, and we could add other variables and so on. Okay, and if we do it, we are going to get a relative popularity versus other cases, because we could have something that made in 5. So let this run. Okay, so this has been run as a regression model. So here's our model specification, and here we have the estimated parameters. Here we have the results for t-students test, and we can see that all the parameters are statistically significant. We have so they're statistically significantly different from 0. We have all the parameters, and what we see, a typical popularity, if it's not any of those categories, 81, and it looks like the mate in 4 and mate in 5 is basically increasing the popularity of the puzzle. So it looks like people are more tending to upvote puzzles which are made in 4, made in 5. But on the other hand, the puzzles that do not fall into any of this category are downvoted. So we do not know why, and it's something further to explore. This is popularity of the puzzle. So if you upvote the puzzle, so from this, it means that people think that puzzles that are long, like mate in 4 or mate in 5, they are very complex, and they upvote them. They more likely upvote them. Kind of strange. I would think that people like more puzzles made in 2, made in 3. But this is, of course, all relative to the puzzle that does not have any of these categories. Okay, because this is a regression model, and here we have estimation of parameters of such a regression model. So this is here being shown as a text output. Sometimes for further processing, we might want to change it to a data frame. So manipulation of data frames is kind of more comfortable. So you can take data frame, and then you have coefficient table set of those coefficient model, and you have is a data frame. So coef table is probably making something from the tables.gl interface, and you need to wrap it around as a data frame, so it's nicely seen as a data frame. So Another question could we ask, does the opening family, or we could also, does the opening family affect puzzle popularity? So are there some openings which make game kind of more enjoying and more stressful, and they result in more exciting ending position before giving the mate? We already knew that most of the games are mid-game, so it's somehow affecting how the pieces are being laid out on the board. So we can do it. So what do? We take a data frame and we group it by. So group by is grouping. So it's converting data frames into several groups. So we have group by data frame, and we are grouping this by opening family. What do we get? We get a group data frame object, which is again not materialized. So the underlying materialized data structure is the data frame, but group data frame is a kind of view over the data. And it has 147 groups because we have 147 opening family values. So we have 147 groups. And each group has few thousand rows. Like we have first group, 4,000 rows. Of course, not everything can be seen. Then we have last group is 7,000 rows. So of course we have 147 groups, but again, it's very smart how the data is being displayed. You have those dots and so on. So we are seeing here it very nicely. Okay. So now what we want to do, we want to calculate, aggregate on those groups. So typical pattern when working with data frames, with data, would be group by, then combine by calculating some aggregates. So what we want to do, we want to calculate what is the average popularity over each group. So what I do combine. I take this data frame. I say add a new column, popularity mean, where it's mean. And what I'm getting a new data frame when I have this opening of family and the average popularity. And that's it. Now, so this macro is a part of language, of broader language for manipulating data frames. You can there will be also different examples because you can use either the standard programming interface or you can use the macro system. So for example, here we have a chain. So if you have a group data frame, and on this group of data, you need to do a series of various commands. So you need to combine, sort, recalculate, and so on. You can combine all those commands. This is via the chain macro. And so the syntax is the following. So chain on those commands. So this is GDF is the group data frame. So it's all our data divided into those groups. And then this is a block of code. So this must be a begin and end. And first we combine it by popularity. And then secondly, we sort it by the reverse popularity. And then we see which openings are the most popular one. Why? What is hippopotamus defense? I don't know this one. Okay, so we have the most we have the most popular opening. We also might think, oh, what did I do that didn't work? I think I forgot here to press this. I'm going to all this and not running them. Okay, so I created all those groups. Okay, and then we have I can also calculate more values. So I could see what is the variance of popularity and how those differences are statistically significant. So now if I take this popularity, so I can see I can see again, so describe is calculating me all the statistics. And again, I can see what is the mean popularity and what is the count of values. Then later, I could, for example, take the so here for each defense, for each game being played, I have popularity and the number of times that has been played. So count is the count is the number of times it has been played. So some game has been played only once, another, the most popular opening, has been played 98 times. And I might want to see how the popularity is related, to the number of plays. And probably when I look for this, so this is so one is popularity and the number of plays, and probably it's not too much affected. So total mean popularity, mean average of popularity is 82, and if I plot this on picture, I can see that the variance is lower with this. The popularity variance is higher with lower number of plays, but maybe this is something to be expected. This is how variance works, and this is decreasing further. Okay, so then what we could do, we can calculate popularity frequency. So we have aggregated popularity count, and we take all those elements which are lower than which are greater than the median popularity value. So we can calculate here several statistics. So now we have another. So now we have another plot. We have frequency. Of popularity versus the number of plays. Okay, I didn't press Control Enter somewhere previously. Did I get? Okay, so the next thing we can calculate is the z-score, so the difference difference between observed popularity and the total value multiplied by the standard divided by the standard deviation. Okay, this is more and more examples. And and then we have then we could have another scatter plot explaining how the popularity depends on the number of how the popularity depends on the number of plays. But what we can see is when looking those results, it's hard to say that there is some strong dependence about the number of plays and the popularity of those puzzles. Okay, there were many examples. So one thing I also wanted to discuss is how the macro system is working. But are there any questions so far? Because there is also, I could do more examples with the data frames. Yeah. Okay, so we have those groups. So you can, of course, chain operations like it was shown, but you can also access individual groups. Okay, so I will just add a cell here. So we had this. So we have this group data frame which has 147 groups, and basically, if you want just manipulate separate groups, what you can do if you do collect. So group data frame is essentially an iterator. So if you do all the groups, you get an iterator object, and you can navigate through all elements of that iterator object. So if I do a collect on that, why it's highlighting, I don't know. So if you do a collect on that, we get a vector of elements. And then if you want, for example, group number 2, of course, normally you have iterator and you are going through elements. Normally you would write a for loop. But suppose I want the data frame, so I want a group, say 3. Okay, so I have a group 3. So I could name it such as df2. And what you can see here, we are getting a sub-data frame. So this is a view of the original data frame onto some set of rows. And then it's just a data frame. Even if I don't want to see the data frame, I could make a copy of it and say it's a data frame. And then I have it as data frame. So essentially, if you do group by, you are getting a long list of data frames. So this all complicated types, and these are well, I think it's relating that it's not materialized. So each time Julia is trying to be, somehow clever about non-materializing all those objects. Okay, so now maybe so of course there will be much more examples with various data sets. So one thing also worth noting, if we have a data frame like this one, there is a Julia data package which is called CSV. So having any data frame, we can of course we can of course write it. We can of course write it into We can, of course, write it into any file. So we can provide CSV write, CSV read, and basically several database formats, several other external data formats are supported. But one thing I wanted to tell you about, because now I think it's a good time. So I spent quite a lot of time talking about, I've spent quite a lot of time showing you different macros. So let us have a small look what is this macro. So we've been writing something, for example, like x equals 7 and show x. Okay, and there are of course many type of macros. So macros are kind of, and you could also see it here on many occasions. So macros in Julia are special programs that take some code as an input and are producing another slice of code as the output. And we can indeed see what is happening because we have a special command macro expand. And I could write something like macro expand show 5. And then what we are going to see, I don't want to show 5. Okay, so what a macro is doing, if it takes a piece of code, so 5 is just a piece of code that is 5. So it might be in a minute do something, we might in a minute do something more complicated. So what do we do? We take a piece of code such as one here, and and are processing are processing one piece of code into another. So now let's have something. Let's have something more maybe complicated. So we have a time macro. So time macro is being used for time in the code. So assume we need to time, say, minimum of around 10,000. Okay, so a small piece of code. Of course, there could be any function. It could be begin, end, block, and so on. So what's going to happen? This piece of code with the timing macro is going to be transported into another piece of code that there will be some variable. Those variables have special names constructed in such a way that they do not interfere into variable names in Julia. So it's generating a special variable name, and it's taking the current time in nanoseconds. It's taking the current time in nanoseconds, and so on and so on. So what you can see, of course, it's quite obvious how to do timing, but you can see there are those instructions. So what you can see, macro in Julia is a very clever piece of code that it's taking one portion of code and producing another out of it. And I think that even I have this code. So code in Julia, there are a few ways to show such code. If I load library using abstract trees, then I think I have command like print tree. No, it doesn't work here. Okay, it works, but it's slightly too big. Okay, any piece of code. Maybe I will take something easier. So let me code to equals, say, macro expand, just show X a simple code. Okay, so any piece of Julia code, oh, it prints twice, so that's why it looks like this. But any piece of Julia code can be represented as a tree. Any piece of Julia code can be represented as a tree of calls. Now, it doesn't look as nice as I want it to. Because this is also slightly, I have in other slides, so just let me open it, because this one lecture here is very, very long. And that's why I started. I forgot the name of the comment. Let me check. I think I've been talking quite long today and blah, 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 blah. Okay. So I will slightly, oh, it's dump. It's dump, and it's the next comment I wanted. Okay. So if you have a piece of code like this, so this is this time. Okay, I will use this short one. So if you have any piece of code, I could use dump. So I just present the underlying object. And essentially, a piece of code is in Julia is represented as a data structure in Julia. So this is a bunch of expressions. So this is a bunch of expressions. Each expression has a head and arguments. Okay, so if you write any piece of code, so we could also maybe even write like quote. This quote, it creates a code block without executing it, say x equals 5 and okay, so if I have a block of code, it says here's head is start of the block of code, and then line number node is for debugging, and so I have the line number, and I have an expression. So the expression, it's a symbol equals x and 5 or so on. So the point is, any piece of code in Julia can be represented as Julia data structures. Okay, so any piece of code in Julia can be represented as the Julia data structure. And if we are writing macros, then indeed what we do, we are writing pieces, we are writing programs that are transforming one piece of code to another piece of code. So I could do something like, say, macro f from x. Okay, and if I try to do macro, I need to write a function that is yielding another portion of code. So it assumes x is some code. I don't know what is x, so it can be whatever, and it's yielding another code. So I could, for example, do a macro quote. So quote is a block of code. So now this macro, so return in Julia is optional, so I could put it here or not. Okay, so now this macro is taking whatever is in X and yielding a piece of code. And I could, for example, do, okay, this will be hello world example. Okay, so it's going to take whatever is inside in X and produce another piece of Julia code. Then this, whatever is inside of Wix, will be wrapped around with this another piece of Julia code. Okay, and if I do it, if I now check what it's doing, f from 3 plus 3, now it's at, okay, 43. So basically, it's taking this piece of code and transforming it into another piece of code. Now, this is something very powerful because this is type of processing which is happening during the compile time. If you remember this introductory lecture, I still have it here, then you have a source, you have Julia source tokenization, then you have abstract syntax tree. Abstract syntax tree is transforming a piece of code to a hierarchical tree structure that like the one that is presented here. Okay, so this is an abstract. So this is an abstract syntax tree. This is an abstract syntax tree from the code. Then if you write macro systems, macros are operating on AST. And in several applications, and we'll be see later, you'll be see later more macros. In several applications, this means you can write some piece of Julia code, and you can kind of provide compiler instructions that during the compilations, this Julia code will be processed into different Julia code. What it means that in some cases, you can offset some part of the computations on the compiler. Okay, because what is happening? Because what is happening? This code goes through the macro, and the macro is executed at the compile time, not at the runtime. Okay, and the macro is processing our code into another piece of code, and then something else is being processed, and the process code goes for the compilation. It's very convenient. It's very convenient because it makes it possible to build several new languages on the top of Julia, or several domain-specific languages, like there was some part of language for manipulation of data frame, or for example, we could have languages or for benchmarking and for testing code. So one package also for benchmarking is named benchmark tools. We'll be using it at also some other lectures. And then here, for example, we can do add b time and a piece of code. So again, this piece of code will be modified into another piece of code, will be wrapped around with a block of code, and this newly generated code is going to be executed. Okay, so this is more or less this is how the macro system works. It's sometimes tricky because what you are seeing in a macro is indeed this X. If I do this X, it can be any block of Julia code. And of course, having such Julia code, you can navigate over it, but sometimes difficult things happen. Like for example, you could have variables, and you could have variables that exist in the macro, but otherwise variables exist in the code, and so on. But this is quite a powerful system. Okay, so do you have any questions? I think I finished slightly earlier than I planned. So do you have any questions at this minute? Or maybe let's do it like this. That maybe it's now. Let's finish the formal lecture, and maybe if you want to chat or talk about some other subjects for a few minutes, because maybe somebody has individual questions in the chat room, so this would be the time then. Okay, very good question. Yes, how do I create a virtual environment? Basically, this is the question. So suppose I'm in some folder. So the question is how to create virtual environment. So suppose I'm in some folder, then I create my project. Okay, and do cd my project. And what can I do when I run Julia? Okay, and I activate the local folder. So it's activating the project. And basically, I'm starting with empty project. As long as it's empty, it's an empty project Tom file. But a Julia project, a Julia virtual environment is essentially any folder in the drive. And if I add any package to this, so suppose I want to add test package, there is a package with such a name. It might be update. I hope it will be not updating Julia too much. Okay, if I add anything, then now I'm going to see two files in this folder. So I'm going now to see manifest file and project Tom. So the project Tom file is now, it's already created. So it's just containing this single dependence that I have added. And the manifest Tom is going to contain all the package dependencies. Okay, so you normally create the virtual environment from the package manager. Of course, you can load the package which is named PKJ, and you can use the PKJ package to manage the environment. Okay, so this was the question. Any more questions we have? Okay, then thank you very much, and maybe some individual questions or individual talks, and we see each other tomorrow at 11 a.m. and then it will be the classes by the next set of teachers, and we'll be talking about predictive models and machine learning in Julia. On the day 3, we'll be talking about numerical methods and optimization problems. So this will be like mixed integer linear programming and this type of optimization models. Then day 4, it will be differential equations, and in the end, it will be distributed computing, so scaling out computations in Julia. Okay, so thank you very much for attending today's lecture, and now maybe if there are some individual questions, then we can talk. Thank you very much.